Welcome to the Thomistic Institute podcast. Our mission is to promote the Catholic intellectual tradition in the university, the church, and the wider public square. The lectures on this podcast are organized by university students at Thomistic Institute chapters around the world. To learn more and to attend these events, visit us at thomisticinstitute.org.
My thanks for the invitation to be here with you, and my thanks to all of you for coming and being here tonight. I've presented actually for this chapter of the Thomistic Institute before, but it was several years ago during COVID, so this is a much better experience of Ithaca than doing it over Zoom. Before I speak about any questions concerning science or touch upon anything having to do with contemporary philosophy of science, I should just begin up front with an admission. First, I'm not a trained scientist. I actually asked Zach if he would ask how many of you are in the sciences, and I feel like I'm in front of the firing line now, which is good. It's a good place to be. But I'm not a trained scientist, and even contemporary philosophy of science is, for me, at best, something that I could put down on my CV as an area of competence rather than an area of specialization. The Thomist, upon whose thought I'm going to depend to a great extent in this presentation, the Dominican Father William Wallace, offers the warning in several places, and also offered it personally to a few friends of mine, that those who don't have significant training in the sciences really ought not venture too far into questions in philosophy of science or questions concerning the reconciliation and integration of Aristotelian and Thomistic philosophy of nature with contemporary science. So I'm going to be treading very carefully with Father Wallace as one of my principal guides. I ask for your patience for any glaring faux pas as I refer to the work of contemporary science or to the work of practicing scientists. I also want to be clear up front that I'm not claiming any particular originality in the content of what's going to follow in this lecture. I'm presenting, for the most part, views of St. Thomas, views of Aristotle that are in no way controversial as far as getting basically right what Aristotle and St. Thomas think, even if the ideas themselves are very controversial. These views concern questions about what science is, what status scientific knowledge has with respect to certainty, and how scientific inquiry is supposed to arrive at certainty through what Aristotle and Thomas call demonstration. But I'm also going to be distilling and summarizing many of the key claims advanced by Father William Wallace concerning the possibility of achieving demonstrative knowledge concerning at least some discoveries made by the sciences from roughly the 14th up through the middle of the 20th centuries. These are views that Father Wallace presents in his book, The Modeling of Nature, so just consider this lecture a long advertisement for a favorite book of mine. Okay. All right, before we begin, we should say something just about the notion of certainty. What do we mean by certainty in raising the question about whether we achieve certainty in scientific inquiry? Well, if by certainty we're only talking about one's psychological attitude towards a particular belief, so if I were to believe that the moon is made of cheese, and then I were also to believe that this belief is itself indubitable or infallible, then one might think that as a psychological matter, you could say that I have certainty concerning that belief, but then you're just talking about my sort of personal attitude towards one of my beliefs. Okay? And it turns out in that case, if that's what we mean by certainty, one can have certainty and yet be horribly wrong about the thing that one thinks one is certain about. So what we're after, more importantly, in thinking about the question of certainty is not primarily the attitude, the psychological attitude of someone towards one or another of their beliefs. Rather, what we're interested in is the sort of knowledge that, if possessed, should leave one without doubt. The sort of knowledge that if you have it, it's a natural consequence of having it that you should be without doubt concerning that thing that you know. But one thing that's interesting about certainty understood in this way is that you could have certain knowledge and yet psychologically not be fully certain and confident. Okay, and this is going to be an important theme for Father Wallace a little bit later. This is a point that will be more helpful when we turn to discussing St. Thomas directly. But it's also helpful just to begin by noting that certus in Latin fundamentally means just being fixed or established or settled. One has certitudo, certitude, when one possesses knowledge about something in such a way that one no longer entertains an opposite view. The mind rests because it has now settled on the truth of something. Okay? So if the idea of certainty is the idea of knowledge having become somehow settled, the mind somehow resting in the answer to a given question, that's maybe a more helpful notion for thinking about what's meant by certainty when we get to St. Thomas, rather than focusing on, indubitability or, infallibility. Okay. All right, I want to begin by rehearsing what I would take to be a fairly typical popular narrative now concerning the relationship between science and certainty, one found among and informing the work of, I take it, many working scientists. I think this is a narrative that comes out of developments and discussions in 20th century philosophy of science. It's a way of thinking about the possibility of certainty in scientific inquiry that I think informs the work of many practicing scientists. But as there are many people working in the sciences in the room, I will I think I'm getting this narrative right. But I might actually be pleasantly surprised if I'm not. So if I'm getting it wrong, please tell me. Okay. I'm then, after I've introduced this kind of popular narrative about the relationship between science and certainty, I'm going to do a little bit to unpack some of the views in the history of philosophy of science and a little bit in the history of the philosophy of science over the 20th century, over the course of the 20th century, that I think forms the appropriate background for understanding how this narrative evolved. All right, so here's the common typical view, I take it. Science does not aim at or result in certainty, and to suppose that certainty is the goal of scientific inquiry is just to misunderstand science and the character of scientific progress. Okay. At this point, I'm hoping I hear at least nods of acknowledgement, right, concerning this view. Okay. Now, there are a number of reasons for denying that certainty is the goal of scientific inquiry. Because scientific work operates on the theoretical side by the positing of hypotheses or theories with testable consequences, such that they can be falsified through experiment and observation, and because the data afforded through experimentation and observation are always underdetermined in relationship to possible rival theoretical models or hypotheses, whatever confidence we have in the adequacy of a given hypothesis or theory or even major theoretical framework for predicting observations, whatever level of confidence we might have, we must always be open to the possibility of some major revision in our hypotheses and theories, and even to our major theoretical framework. So, as, again, the common narrative goes. Now, the very history of science indicates something of the need for such openness to major revisions. As we went, this is the usual example given for defending this sort of narrative. We went from once thinking with Aristotle that gravity is an intrinsic propensity of a heavy body towards its natural place in the center of the universe, to later thinking about gravity as an attractive force between bodies in direct proportion to their masses and inversely proportional to the square of the distance between their centers, to later thinking about gravity in terms of the curvature of space-time, to the situation in which some theorists expect or hope for revolutionary developments in the field of quantum gravity. On the side of experiments and observations themselves, uncertainty and error are ineliminable from quantified measurements, such that the empirical foundations of scientific inquiry require, one might say, some comfort with uncertainty from the get-go. Although I'm going to bring this point up later, it's important to distinguish between certainty and precision, and concern about on the side of measurement has more to do with issues of precision than uncertainty. Okay. All right, so now I want to sketch just a few basic notions or positions in contemporary philosophy of science to provide a little bit of philosophical background and elaboration concerning some of the elements of what I've just called the popular narrative, the common narrative, about the lack of certainty in the sciences. First, we have to pose this question: about what would we claim to have certainty in the first place as a result of scientific inquiry? Is it certainty about the truth of our theories or laws or theoretical frameworks, like the theory of general relativity or the theory of inflation in cosmology, or the theory of neo-Darwinian evolution, or the periodic law in chemistry? Or would it be certainty somehow about our measurements? Or would it be certainty about our ability just to predict particular phenomena? Or would it be certainty about sentences like the following: the moon is roughly spherical, or the proportion of atomic hydrogen and atomic oxygen in water is 2-to-1, or blood circulates in the human body, driven by the pumping of the heart? Okay, so if we were to claim to have certainty, certain knowledge as a result of scientific inquiry, what would be the object of that certainty? Now, I select those particular examples of sentences because we're going to mention them again with Father Wallace as examples of scientific truths that he thinks we can properly say we have certainty. Okay, but we'll come back to that a bit later. Okay, so there's this question about what do we claim to have certainty about? What would we claim to have certainty about as a result of scientific inquiry? Okay. Another important question, and a question that's really at the heart of a lot of the debates in 20th century philosophy of science, is the question of whether we would ever claim to have some kind of knowledge, certain or otherwise, concerning the existence of the theoretical entities posited in our theories. Our theories, and especially our physical theories, posit numerous unobservable entities and forces, like the electron and the electromagnetic force. Does the knowledge resulting from scientific inquiry ever result in knowing that such unobservable entities actually exist? That is, that words like electron actually successfully refer to an entity that exists in the world, the way that the word dog successfully refers to Fido. Here, the specter of logical positivism or logical empiricism, like that of Rudolf Carnap, looms large. A view from the middle of the 20th century that, in broad brushstrokes, holds that terms for theoretical entities like the electron are just not to be taken literally so that they would refer to distinct existent entities. Rather, terms for such theoretical entities even have their meaning. So this is a theory about the very semantics of theoretical terms. Theoretical terms have their meaning only by association with observable entities. So for the logical positivists, electron might actually just mean visible streak in a vapor chamber, okay? And all of the theoretical notions attributed to the electron as a theoretical entity for explaining what's observed, you don't posit that anything like that actually exists. You just have an entity in your model that successfully helps you predict what you actually observe. Okay. So logical positivism, logical empiricism has as its antecedent ultimately the empiricism of David Hume, where all ideas to genuinely be ideas of the human mind have to be reduced to our sense impressions, right? Have to be reduced by association to things that in fact we directly observe. Now, the obviously anti-metaphysical orientation of logical positivism or logical empiricism is such that no non-observable entity is ever to be posited, or even such terms are not to be regarded as having any meaning, except according to this kind of association with an observable. So on this view, the word God is definitely out. Okay? Now this, of course, raises the question that we've just employed some sort of distinction between the observable and the unobservable. So this raises the question, what is the boundary between the observable and the unobservable? Now, in philosophy of science, in discussions of various views about realism, anti-realism, and philosophy of science, the boundary between the observable and the unobservable is typically regarded rather strictly. Things only count as observable if they are observable under ordinary circumstances or conditions by the unaided senses. So it's a fairly narrow list of things. And even if you have to use a telescope to do it, that strictly speaking doesn't count as an observable. Okay, and that's an issue that's going to come up again later. Okay. Now, a modified form of empiricism, the constructive empiricism put forward by Voss von Frossen, is willing to allow that theoretical entities within a model might actually refer to real entities. Such terms could have a meaning that's not just reducible to mere association with observables. But nevertheless, this view holds that we always have to remain purely agnostic about whether such entities actually exist. So it's like an improvement on the semantic theory. Yeah, look, electron, when we talk about electrons, we're talking about things as if they exist within atoms and molecules that have all of these characteristics, but we actually should be agnostic about whether the things in fact exist, whether the words actually successfully refer. Now, logical empiricism falls more broadly under the heading of what are usually called instrumentalist views concerning scientific theory and method. For instrumentalism broadly, all that matters is that a model successfully saves the appearances. This is what we use theoretical models for. We try to predict what we're going to observe. And one simply should not posit the actual existence of any theoretical entity on the basis of such predictive success. And the figure most famously associated with the broad position of instrumentalism in science is Pierre Duhem. Okay. Now, the recognition that even major theoretical frameworks do undergo significant revisions or even abandonment in favor of new theoretical frameworks led Thomas Kuhn in the middle of the 20th century in his The Structure of Scientific Revolutions to characterize the entire methodology and history of science in terms of paradigms. Paradigms generate the ordinary questions for investigation in periods of what Kuhn calls normal science. But the history of science is also marked by revolutionary paradigm shifts, which occur when a given paradigm's failure to adequately solve problems and to account for new observations requires a radical rethinking of the theoretical framework according to which ordinary scientific questions are articulated. Importantly for Kuhn, the incommensurability between competing scientific paradigms is, on his view, such that one can never perfectly translate everything from one paradigm into a competing paradigm, and consequently, one can never regard a given paradigm shift as approximating more closely to or moving farther away from scientific truth. That's just an ill-formed thought, right, for Kuhn. It's just, we've got more observations that check out, and that's it. But to suppose that paradigm shifts in the history of science get us closer to the real truth about the natural world, that Kuhn thinks that's nonsense. Okay. All right, now finally, though, in recent decades, a greater number of people working in contemporary philosophy of science have begun to put forward various versions of what they call scientific realism. For many of these figures, then, theoretical terms can successfully refer to unobservable entities. It would only be for someone holding to some form of scientific realism that one could, for example, as Father Thomas Davenport suggested in a recent Thomistic Institute lecture, one could hold it to be certain that protons exist. Okay. Now, the reason I bring up these various, and I know it's very broad brushstrokes very quickly, but competing views in 20th century contemporary philosophy of science, is that the very question about what would you be certain about in the first place is radically different according to these competing visions about science and scientific method, right? If you think that all you ever do is make predictions about observations and you never commit yourself to the existence of anything posited in any theoretical model, well, I mean, what would you be certain about in the first place? Just that your model works, okay? You wouldn't claim to have some certainty about the way that the world is on the basis of that view about the purpose of science, okay? Now, the popular or typical narrative that I recounted before concerning the impossibility of attaining certainty in science, or the thought that you're doing it wrong if you're concerned with trying to arrive at certainty. This has its roots to a great extent in the various views adopted by philosophers of science over the course of the 20th century. because people are familiar to some extent with the views of various figures mentioned, like Duhem, Karl Popper, and Thomas Kuhn. But at a more fundamental level, the popular narrative concerning the limits of science, the limits of scientific methodology, is also grounded in what continues to be the popular understanding of the core methodology of science, which, despite the continued debates among philosophers of science about scientific method in the later part of the 20th century, still continues fundamentally to be, and this is another point where I'd like to be corrected if I'm wrong in terms of common views among people working in the sciences. The common understanding of the core methodology of science continues to be the hypothetico-deductive confirmationism advocated by Wool in the 19th century and by many figures in the 20th century prior to Popper and Kuhn. Okay. At this point, and here I'm leaning quite a bit on Father Wallace's presentation, we need to sketch a few logical forms so as to articulate the common understanding of the methodology of science. Okay, so if P then Q, okay, P, therefore Q, okay, usually called modus ponens, okay, and a valid form of reasoning, okay. All right, most of these are going to begin with if P then Q, okay. Let's see which one I put second here, though, okay. All right, not Q. Therefore, not P, okay, usually called modus tollens, okay, another valid form of scientific reasoning. Okay, now we've got the two fallacies. All right, so these are just the four basic forms in conditional logic. The first two are valid. These are both invalid. Okay. Usual understanding of the method of science. Which one of these does the usual understanding of the method of science, right? You've got a hypothesis or theory, you make a prediction, you see if you observe it. If you observe it, it supports your hypothesis. Which form is that? Yeah. Which one? No, because your hypothesis is this. If your hypothesis is true, you expect to observe this, right? You don't observe the truth of your hypothesis. You're investigating whether Q is true, right? Okay. So the one in which you observe that you actually see what you expected to see is this one. It's an invalid form of reasoning. Now, everybody knows, like the philosophers of science who articulated and in the 19th century put forward the theory of confirmationism, they know this about conditional logic, right, that this is a fallacy. But then that's why this alone doesn't actually constitute what's usually called the hypothetico-deductive method. Okay, so there's a little bit more to it. Okay, all right, this one actually doesn't work, but if you modify it a little bit, you can do this. You can say, well, if P then Q, if this hypothesis is correct, I expect to observe Q. I do, in fact, observe Q. Therefore, it's at least possibly true. Okay. Now, I don't know. You don't seem like you're that much better off than you were before the experiment, though, because presumably you already thought the hypothesis was possibly true. Okay. So even better is this. And this is where you get the idea of probability and confidence entering in, okay, in the expression of scientific conclusions. Okay, if P then Q, oh sorry, not just Q. If P then Q, Q1 and Q2 and Q3, and so on up to Q sub n. Okay, but in fact you observe Q1. Q2, Q3, and so on. Okay, and it's at this point you are justified in saying probably P. Probably. Okay, now this is a point where I remind you I'm not an expert in contemporary philosophy of science or a working scientist, so ask me nothing about quantifying probability here. Okay? But when you express how much confidence you have in a given hypothesis, it's a function of, right, the number of testable consequences, not just of that hypothesis, but of that hypothesis along with all the other hypotheses that kind of go with it within a theoretical framework. Okay. All right. This is the method that's usually called hypothetico-deductive reasoning. Okay. And it is valid. Okay. So the fundamental reason logically why we say scientific reasoning, the logic of scientific discovery, doesn't result in certainty is because we understand the scientific method in terms of this logical form. That's why. Okay? And it's the right answer. If this is the only logic of scientific discovery, then scientific inquiry does not result in certainty. Okay? Except in one other place. Okay?
Number 2?
Yeah, number 2. What's number 2? What's the... Yeah, exactly. So, and this is going to be what Popper emphasizes, right, as the fundamental method of science is falsification. Okay, we can't be certain about the truth of our hypotheses, but we can be certain about the falsity of bad hypotheses. And that's a way for science to make progress. You do have certainty about something. Okay. Again, now Popper is within the broad tradition of logical empiricism. He still has these semantic views about theoretical entities and all of that. All he's saying is that that some hypotheses don't work. And you're certain. They're out. Okay? And that's something. That's not nothing. Okay? Until critics of Popper come along and point out the following. This is primarily pointed out directly in response to Popper by Quine, but it's a point that had already been raised by Pierre Duhem much earlier in the 20th century. We've got this form. Well, think about it this way. How many assumptions do you actually make when you set up an experiment and you make your prediction about what you're going to observe? Is there actually only one sentence informing the prediction that you make about what you're going to observe, right? There are all sorts of assumptions that you make, even just about your theoretical apparatus, about your experimental apparatus, and that it's functioning correctly, right? Okay, so there's all sorts of other things that you assume. So the criticism is that what's actually going on is this. If P1, P2, P3, P sub n, then Q. Okay. But not Q. Okay, therefore, not P, but which one? Okay, like which one is excluded, which one is falsified. Okay, so this is what's usually referred to, the thought behind what's expressed in this logical form is usually now called the Quine-Duhem thesis. And it's just an observation that there's actually also just probability and confidence even in falsification, right? Because you have to have a reason for asserting which one of your hypotheses is ruled out, right, by not observing what you predicted that you'd observe. Okay. All right, one final form, and this is going to be how I make the transition to talking about Father Wallace. If you could know if and only if P, then Q, then the observation of Q would validly give you the conclusion P. Okay? So the question is, under what circumstances, if any, are you in a position to know that the hypothesis and what you expect to result from the hypothesis, in fact, are interchangeable or convertible with one another? Such that if this is true, right, then such and such results, and not only that, but if such and such is a result, it could only be because of this particular explanation. Okay. All right, so the point of all this is that so long as the logic of scientific discovery or justification is understood in terms of hypothetico-deductive reasoning, or even in terms of falsification, once you have the Quine-Duhem thesis, then it seems clear that scientific conclusions are not going to be certain, but only ever probable, even if extremely probable, and a matter of extremely high confidence. It's for this reason that Father Wallace, in order to defend the Aristotelian notion that scientific inquiry can result in certain knowledge, appeals to the logic of demonstrative argument articulated by Aristotle and developed within the Aristotelian tradition. All right, at this point, I'm going to quickly introduce some core ideas from Aristotle and Thomas concerning their philosophy of science, their philosophical account of scientific methodology. It's going to be very broad brushstrokes, very quick. But the very notion of science is, for Aristotle and Thomas, marked by certainty. Definitionally, for Aristotle, science is certain knowledge concerning something universal and necessary, resulting from demonstration, where demonstration is a proof in which one proceeds from things that one already knows and knows with certainty to knowing a conclusion with certainty. So this is just a terminological point, just as a matter of terminology given this definition of science. For the Aristotelian or the Thomist, as soon as one abandons the idea that scientific inquiry can aim at or result in certainty, one has actually just given up on the classical notion of science. Okay? One has given up on the notion that inquiry ever results in science in the strict sense. Now, for Aristotle and Thomas, science results from what Aristotle calls demonstration, an argument ideally in syllogistic form in the first figure. So rather than fundamentally expressed in conditional logic, better fundamentally expressed in four-term syllogistic form, like B is C, A is B, therefore A is C. An argument in this form in which one reasons either from an effect to the existence or the mere fact of some cause, or one reasons from a known cause to an effect. On this account of science and scientific certainty, that about which one has scientific certainty is always the conclusion of such an argument. Okay. So I raised the question before, if you ask, does science result in certainty? There's the question, well, what would you have certainty about? Right? Is it going to be theory? Is it going to be measurement? Is it going to be the ability to predict? On the Aristotelian view, no, it's always going to be a sentence of the form A is C, S is P. Okay. All right. Let me give two examples here. Okay. That was harder to move than expected. Okay. Let me give two examples here that Aristotle gives of something in the form of a demonstrative syllogism, but something that he doesn't actually think these are good demonstrations. So I'll explain why in a second, but explain why he still gives these examples. So these are examples from Aristotle's posterior analytics. Okay, they go as following. Every body that does not twinkle is near. The planets do not twinkle. Therefore, the planets are near. Okay. Now, Aristotle puts this forward as an example, not because he thinks it's a good explanation of the nearness of the planets or of the non-twinkling status of the planets, okay, in comparison to the stars that do twinkle. Other astronomers had put this forward as an explanation for why the planets don't twinkle, okay? But he gives it as an example because he thinks it's really obvious if a demonstrative argument for a conclusion always goes either from cause to effect or from effect to cause. He thinks it's really obvious which one this would be. So if this were the right explanation of what's going on, would this be cause to effect or effect to cause? You think to cause? Yeah, why? Okay, so what we're doing is we're presupposing that for some reason just being close to the Earth has something to do with a heavenly body not twinkling. Okay? Okay. If there's any such relationship, right, it would go in this direction, because it would be especially absurd to suggest that the very fact of not twinkling is the reason why something is close. Right? Whereas it makes sense to suppose, if this were a causal explanation, that being close would be the reason why a thing appears in a certain way. Okay? Okay. So what's being presupposed here is, certain claims about the relationship between physical location and appearance, right? The way something appears is never the cause of its location, but its location can be the cause of the way that it appears. Okay? So what Aristotle does is to take this, again, in his mind, not a great example of a scientific argument, and he rearranges it, okay, to say every body that is near does not twinkle. The planets are near. Okay, therefore, the planets do not twinkle. Okay, in this case, again, if it were a good causal explanation, we would now clearly be moving from the thing that is the cause to the thing that is the effect. Okay. All right, the name that Aristotle gives for a demonstration that moves from cause to effect, he calls it, well, we call it in Latin, a demonstration propter quid. And a demonstration that merely goes from effect to cause, we call a demonstration quia. Quia just means that, okay? So in one case, you could know just that something is true. In the other case, you really are expressing your understanding of why it's true, okay? When you're able to arrange things in the order that moves from cause to effect. Okay, again, for Aristotle, these are not actually examples of sound demonstrations. This is not his view about what the cause of the non-twinkling of the planets is. But it was an explanation that had been suggested by other astronomers. And Aristotle finds it helpful for illustrating the distinction between effect to cause reasoning and cause to effect reasoning. If there is a causal relationship between distance and twinkling, it's obviously going to go, right, this way rather than the other. Okay. But what this suggests, the other reason he gives this example, is that it suggests the idea that in a given case, we might first reason to a conclusion about the cause from what we first better know about the effect. But as soon as we know that the cause and the effect are convertible with one another, that this cause is the only possible explanation, that the effect necessarily follows, then it's possible to produce a demonstration propter quid from cause to effect. Okay, these are not good examples of actual sound demonstrative scientific syllogisms for Aristotle. Where might we look for examples of demonstrative knowledge in the sciences? Here, we can highlight the dramatically different attitudes of Father Wallace on the one hand concerning the history of science in comparison to the attitude of Thomas Kuhn, who asserts at the very beginning of The Structure of Scientific Revolutions that familiarity with the details of the history of science will only support his view concerning the revolutionary paradigm shifts between incommensurable paradigms. For Wallace, although the history of science does display the revolutionary upheaval from time to time indicated by Kuhn concerning major theoretical frameworks, there are nevertheless particular scientific conclusions reached at various points in the history of science that are truly settled questions concerning which we now entertain no doubt. if this is so, if there are at least some conclusions about the natural world which no one in fact puts into question anymore in any period of what Kuhn calls normal science, then there might be cases in which we actually should be able to give an account of our certainty through the articulation of an Aristotelian demonstration. Now, some of the following examples might seem rather trivial. Okay? And I think the question about whether we in fact achieve certainty through scientific inquiry is tied up very much with how we think about the work of scientific inquiry as always sort of at the leading edge, right? Always concerned with the things that we don't yet know. We don't necessarily spend a lot of time reflecting on why we in fact know the questions that we regard as having been settled for a long time. Okay? So some of these examples might seem a little bit trivial, very far from the cutting edge questions pursued by the forefront of scientific inquiry. But as Father Wallace notes, quote, "In this matter, where the very possibility of truth and certitude in science is at question, there is no such thing as triviality." If you can give any example of something that's not obvious just by observation alone, that can only be known by a reasoning process, and it's an example of something about which we are certain, we regard it as a completely settled question, no one in any shift in theoretical frameworks takes up the question of whether we should re-examine this particular issue, we should be willing to say that we have certainty concerning that particular point, right? That particular conclusion. Okay. And if we have settled questions, even concerning what might seem to be trivial points, then we should be able to articulate why we have certainty concerning, right, that conclusion. All right, so what Father Wallace does in the later chapters of the Modeling of Nature is to put forward a list of about 10 conclusions reached by science over the course of science from the 14th century up to the middle of the 20th century that he thinks in fact have the status of demonstrated knowledge. Conclusions concerning which he thinks we should say that we have certainty. Okay. Here's his first example. The Earth is roughly spherical. Okay? The Earth is roughly spherical. This is not, for most human beings, a direct observable. It was arguably only a direct observable for the first astronauts who orbited the Earth. But does this mean that we should say that we were not yet quite certain about the rough sphericity of the Earth, even in ancient times? Well, the demonstration would go like this, and this is the sort of demonstration that was given in ancient times for the conclusion that the Earth is roughly a sphere. It would go like this. The Earth is a body from which terrestrial and celestial observations reveal that they are made from a convex spherical surface. And the Earth is a body that casts a circular shadow on the moon during a lunar eclipse. And the Earth is a body to which falling bodies gravitate perpendicularly over the entire surface. But anything having those characteristics is a sphere. There is nothing that has that set of characteristics that is not a sphere. And therefore, we can say that we have certainty that the Earth is a sphere. Okay. Now, what's important there is the conjunction of multiple, right? Multiple properties of the Earth together, observed properties of the Earth together, that together, on Wallace's account, achieve the convertibility with being a sphere. What Wallace does is to go on to detail a number of scientific conclusions from the history of science that he thinks have the status of demonstrated certain knowledge. These include the refraction and reflection through spherical raindrops of sunlight to cause the appearance of the rainbow, something demonstrated by a Dominican named Thomas of Freiburg in the 14th century. The circulation of the blood caused by the pumping of the heart. This was only demonstrated in the 16th century. It was something that Descartes and Bacon got completely wrong. The prevailing view is still the Galilean theory, that there was an organ in the center of the body that produces new blood, and that when blood reaches the end of the arteries, it just sort of gets absorbed into flesh. Okay, that was the prevailing view about what the heart does and what blood does up until the 16th century. And when it was demonstrated by someone who presented his argument in the form of an Aristotelian demonstration. This is also something to be said about Galileo. One of Father Wallace's main objects of attention in the modeling of nature is the scientific methodology of Galileo himself. Galileo understood his own scientific methodology in terms of this account of Aristotelian science and demonstration. Okay. He was influenced by another thinker at the University of Padua, Giacomo Sabarella, who developed a more complete Aristotelian account of how it is that you can justify making the move from first reasoning from the effect to the cause to knowing that the cause and the effect are convertible with one another. This is called the demonstrative regress, or demonstrative regressus. So this is the actual method used by Galileo for his discoveries. He understood in the context of the Aristotelian tradition. So other examples of demonstrated truths given by Father Wallace: the sphericity of the moon and the presence of mountains and valleys and craters on the moon, things that Galileo demonstrated on the basis of observations made with the telescope. The universal gravitation as a cause of the motions of both heavenly bodies and earthly bodies by Newton. And finally, the claim that atoms are components as material causes of molecules according to proportions expressible in chemical formulae, as something demonstrated by science in the 18th and the 19th centuries. So I'll finish with this final point. I think Kuhn is right that the way that you think about the question of progress in science and the question of methodology in science and what science can or can't achieve is very much a function of the way that you look at and understand the history of science. Right? And when you look at the history of science, what you see is the great revolutions and the major theoretical frameworks, right? The, as it were, rethinking of everything, right? Then it looks like, okay, we're not certain about anything. Any hypothesis I put forward could be later revised in the context of a different theoretical framework. But if instead what you do is you just focus on conclusions, you just focus on particular conclusions that have been reached in the history of science that we have never called into question since they have been articulated, and that themselves function as, if a theoretical framework screwed these claims up, it would be out, right? That's where we should be looking for the possibility of achieving certainty within scientific inquiry. Okay, so the attitude that you have towards the history of science does matter quite a bit, okay? And the sort of narrative through which you understand the history of scientific development. I hope this is helpful. Okay, I think for people, for working scientists, presented with these ideas, at first it's like, well, who cares? I mean, they really are kind of trivial examples, right, of things that, the answer is not that everyone's scientific work now is going to result in certainty. But the large project of science can ultimately result in certainty concerning at least some conclusions. Okay? All right. Thank you.
Thanks for listening to this lecture on the Thomistic Institute podcast. The generosity of people like you makes this podcast possible. If you enjoy these talks, please consider showing your support at www.thomisticinstitute.org/donate. Your donation of even $1 helps us reach more college students and many others with the powerful truths of the faith, and it ensures that we can keep publishing top-notch lectures on this podcast. Thanks a lot.